Hi there, welcome back to another video. Today we are looking at file sizes, image and sound calculations. So as part of your paper 2 at AQA or paper 1 with OCR, you will be expected to work out sort of the size of a file based on a series of sort of measurements given. Okay, so some key learning objectives. Basically, I want you to be able to understand the different file sizes used by computers, different measurements that you can get, understand how actually represented to a computer, because we said everything is binary. How does that work when it comes to images? How do we convert sound into binary? And finally, calculate file sizes of both sound and images. Okay, so when we talk about storage sizes, I am just referring to sort of storage sizes we use in computing. But remember, storage sizes are all around us. So, for example, grams, milliliters, miles, kilometers, things like that. So all we are talking about here is storage sizes used by computers. So there is 87.1 gigabyte of 128 gigabytes available. So this is just a typical phone 64 gig. Sometimes they can come in 256. So basically what I'm trying to get across is what this is basically saying is the amount of storage you have literally on this device that's been sort of built in, probably a solid state drive, but we'll get to that later, is 128 gigabytes. That's how much data it can store. And obviously we have stored this much, or we have used up this much, which is equivalent to 87.1 gigabytes. So the smallest sort of storage size or measurement that you can get is a bit, which is either a 1 or a 0. That's a single bit, that is it. That's the smallest version. Then we have byte, so we have 8 bits in a byte, so 8 combinations of zeros and ones would be equal to 1 byte. So you're probably aware of this already, but just like 10 millimeters is equal to 1 centimeter, it is just the same as that, apart from we are talking about bits and bytes. So we are converting all the time between these different storage sizes and basically working out which one is the most appropriate to use. Then we move on to kilobyte. So there's 1,000 bytes in 1 kilobyte, or 8,000 bits if you like. Then we have a megabyte. This is 1,000 again, 1,000 kilobytes in 1 megabyte, 1,000 megabytes in 1 gigabyte, 1,000 gigabytes in 1 terabyte, and so on and so forth. We also have a petabyte. So have a little look at this, maybe pause the video, just make yourself aware of this. You probably have already been taught this, I would hope, but you need to be able to convert between the different measurement types. Okay, so I've got a bit of a task for you. What I'd like you to do is convert the sort of size given into the size asked for. Pause the video now, and I'm going to give you the answers in just a moment. Okay, so here are your answers. If you didn't quite manage that, it's always worth a rewind on this video just to see me talk through them. You will be expected to be able to confidently convert between bits, kilobyte, megabytes, all of it, and that will help you for the rest of this video, so it's really important that you get that. Just for now, what I suggest doing is potentially writing it down in your notes and just having it next to you until it becomes second nature, it's in your long-term memory. So moving on to images, I am a series of zeros and ones being processed by your CPU right now, which is quite weird to think of. How does my device, which is a camera, a webcam, how does that record my voice, my likeness as zeros and ones and portray it to your device, which you're watching me on? Well, let's start with images. So what is a pixel? You've probably heard of what a pixel is. It's the smallest, most addressable part of an image. It's the smallest thing. If you look at any image, a pixel is just a single sort of dot of colour. But that is your exam definition. That is what you need to say in the exam. Okay, so you can see here, on my right hand side, we have something called a low resolution image. That means there's a smaller amount of pixels in this image on the right hand side. This means typically the image is going to be a lot less detailed, it's going to look maybe more digital, whereas we have a high density of pixels in this image on the left hand side, and my image is a lot more like real life. It's being able to be recreated with the correct maybe colours and the correct amount of detail. It's looking a lot more realistic. So a pixel is just one of these squares here. If we have a really small amount of pixels, images become a lot more blocky, looking more like the one on the right here. So how do we work out the size of an image? So I have just a black and white image here. First thing we're going to do is we're going to work out the width and the height. So all I'm going to do is I'm going to count the pixels and work out the total amount of pixels in my image. So 1, 2, 3, 4, 5, 6 pixels across. 1, 2, 3, 4, 5, 6 pixels down. So in this whole image, there is 6 by 6 would give us 36 pixels. Okay, so black and white images, it means we could specify 1 is going to be used for white and 0 is going to be used for black. Happy days, because computers only understand binary, so that fits in really nicely. So in all honesty, I actually only need sort of a color depth. This is the amount of bits that we need to sort of put aside in order to represent the colours. So I actually only need a colour depth of 1. Okay, so the size of this image is going to be the width times height times colour depth. So black is 0, white is 1. That's all I need. I don't need any other sort of bits joined onto this because there's only 2 colours, there's only 2 sort of outcomes there. So all I did there was 2 to the power of 1. That will allow me to work out how many outcomes sort of I need. So the size of this image is 36 bits. Okay, so let's add some more colour. How does that work? Well, I'm going to do the same thing again. I'm going to work out the width times height. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So to work out the total amount of pixels, I'm going to do 5 times 5, which is obviously 25. So I know the pixel density at the moment. Now we have pink, we have white, we have red, we have blue, and we also have yellow in this image. So I have 1, 2, 3, 4, 5 different colours that I need to be able to represent using some sort of bit pattern. So we've already said 2 to the power of 1 is going to be just 2 colours, because that is 2 to the power of 1. 2 to the power of 2 will allow me 4 colours, because basically I am saying I could have 0, 1 to represent a colour, 1, 1, 0, 0, and 1, 0. They are the only combinations I can use when I have a colour depth of 2. Okay, let's try 2 to the power of 3. And all I am doing here is 2 times 2 times 2. Well, 2 times 2 is 4, times 2 is 8. So I can have 8 different combinations of zeros and ones with a bit pattern of 3. So this means I can have 8 different combinations I can use to represent a different colour. So I'm obviously going to choose this one here because 4 is not enough. I have 5 colours to represent. 4 different outcomes is not enough. So I've got to go with 3, even though I have 3 that I won't use. Okay, so 25 is the amount of pixels, and all I need to do is 25 times the color depth, which again is 3. So that is 75 bits used here. That is the size of that image. So if you ever want to work out how many bits the color depth is, all you need to do is count the amount of colors in the image and just see which one fits. Is it 2 to the power of 1? So does it only need 2 colors? 2 to the power of 2. Does it only need 4 colors? 2 to the power of 3. 8 colors, or maybe even more, 2 to the power of 4, which is 16 colors, so on and so forth. Okay, so like I say, rewind the video if you want to watch me go through that again. Maybe put it on a slightly slower speed, do it with me. But now I want you to go through this exam question. So work out the size of this image, give your answer in bytes. Make sure you're not giving it to me in bits. I'll see you in a moment. Okay, so first, obviously, we are going to count the amount of pixels in the image. So we have 6 across, 6 downward. Okay, 6 times 6 is 36, so there's 36 pixels in this image. The color depth is going to be, the color depth, 2 to the power of 1 is only allowing us 2 colors. 2 to the power of 2 is actually going to help us represent 4 colors. So we have 1 color, 2 colors, 3 colors, 4 colors. So the color depth here is 2. So all I'm going to do is 36 times 2, which is 72 bits. Now, we would get 1 mark for this being correct. However, our final mark we are only going to access if we give our answer in bytes. So how many bits in a byte again? Yes, it is 8. So 72 divided by 8 is 9 bytes. Talk about sound. I need you to know that obviously sound comes in the form of a sound wave. So first thing to note is the louder something is, we say the higher the amplitude. So we would typically see in a loud noise, the amplitude would be a lot higher than maybe, let's say, a whisper, something like that. Okay, so that's something to note. When we talk about frequency, so if something is really high pitched, we would see the frequency is a lot closer together. Okay, maybe if something was really low pitched like this, typically the sound wave would be further apart. So a really high pitched noise is going to be very close together and very high on sort of the amplitude sort of measurement. So the important question is, how do we represent a sound wave in binary? That is the question. So I have just a sound wave here. Let's say it's a voice recording. Just take a moment, maybe pause the video. Can you label parts of this diagram already? Okay, so what we have is we have something called amplitude along the side. We've just spoke about this. And then along the bottom, we have presumably seconds. Obviously, this is an analog sound. It's not a digital sound. This is happening, and it is not something that is digitally created. I'm just going to presume it's a voice. What we actually do is we will use an analog to digital converter. So the sound is coming through the microphone, and we have something called an ADC. Okay, so what happens is typically every second, the computer will take a sample. Every single second to see where the frequency and amplitude is, right? So what is happening here is every second I'm just seeing at what point sort of the sound wave is at. Then eventually this is given a bit value, and then the computer is able to recreate this sound wave based on this series of measurements. So if we increase the amount of detail we can have here, so the sample resolution, yes, we are making the file size larger, but we're actually making it more realistic. So there's two key words for you: sample rate. Okay, and sample rate is the number of times an audio signal is actually sampled per second. And then the sample resolution is just the amount of bits that we are using to represent that sample. Okay, so working out a sound file size is similar to working out sort of an image size. So we just literally times everything together. So all you are going to do is you are going to times, obviously we're going to do it in seconds, so a 1 minute 30-second clips, that's going to be 90 seconds total, a sample rate of 1000 hertz and a sample resolution of 2 bits. All you are going to do is times them together. So I'm going to do this now. However, if you want to pause the video and give it a go, it's always worth a try. So we are going to times them all together. So 90 times 1000 times 2. That gives us a total of 180,000 bits. Now, if I wanted to put them into bytes, what calculation am I going to do here? I'm going to divide by 8, which gives us 22,500 bytes. Is that the most appropriate file size I could potentially store something in? Maybe not. I may want to store it in kilobytes. So again, all we are doing is we are looking at the sample rate, sample resolution, and the length of the clip or voice recording, whatever it is, timesing it together and just double checking, have I put this in the correct form that the question is asking me? Okay, so I've got another question for you. I would like you to give it a go, and I'm going to run through it in just a moment. Okay, so a 2-minute voice note. So that is 120 seconds. The sample rate is 4000 hertz and the sample resolution of 6 bits. So all I did was times 120, 4000 and 6, and I got this value here. To get this into sort of bytes, then I'm divided by 8, and then actually, the question was, give your answer in megabytes. So we're still not there yet. This is bytes. The next sort of larger storage size is kilobytes. So I'm going to divide by 1000. And then we're going to divide by 1000 again, which gives us 0.36 megabytes. Okay, hope you found this video useful. Okay, so hope you found this video useful. Just remember, when working out file sizes, the main thing you need to do is make sure you're timesing it all together and just double check you are giving it in the correct form.